Welcome everybody in the lecture hall, welcome everybody on Zoom, welcome everybody from the future. I just have a few slides left with document stores, and then we'll move over to query languages for JSONic, which are cooler than APIs. I have a question for you before that. And the question is, how does a document store like MongoDB store documents physically? Is it as text files, these JSON lines files, because that's collections of JSON objects, right? So it's text files, and MongoDB queries are automatically converted to MapReduce or Spark queries against the data lake on which this is stored. Or an optimized binary format called JSON on the local hard drive, JSON types, arrays, and objects are efficiently stored and basic atomic types are supported. Or is it that text files JSON on the local disk, they are parsed on the fly with a very efficient technique called just-in-time parsing, or using crowdsources, there is a document center under the Antarctic where little elves store and retrieve documents on paper, nicely sorted on shelves organized in racks. And I should start. Of course. That is the demo effect. This one. So indeed, the majority says BSON, the binary format. So indeed, this is how it's done. What I would like to emphasize is that all four answers are actually perfectly fine in terms of data independence, right? As long as you expose collections of documents, query languages. So the four are fine. And if you visited information retrieval, then you know that I have a lot of elves in Antarctica that are very useful for probability theory. Now I'm going to move over to the slides again. These ones. There you go. So I'm almost done actually here. So this is where I left you, where we have this index. Do you remember if it's a hash or a tree index? If I do it in this way, anybody? Tree index, exactly. This is like ascending, descending. And otherwise, that would be the string hash instead of the 1 and -1. So indeed, this is a tree index. More precisely, it's a tree index on a compound key that is made of several JSON fields, birth and death, and then we use the lexicographic order. Again, that kind of hurts a little bit in terms of the JSON model, because normally this is supposed to be no order between birth and death. These are two keys in an object. However, as I told you, it's kind of a leak in the model. So for MongoDB, there is actually an order there in the API, right? So in the API, it does look at the first one and the second one. And so maybe it was a bit of a mystery to some of you why the query below still works, even though it's not exactly the same keys as the index. And I made a new slide for you. This is why. Because when you create an index on a compound key, several of them, let's say A and B, in this order, first A, then B. And imagine that these are all the compound keys. Like I have a collection with 10 different compound keys that I all put in there. When you create an index like that, it basically means first sorted by A, then sorted by B. So you have A1, first all the A1s and then sorted by B, then all the A2, then sorted by B, then all the A3, then sorted by B, right? So it's called the lexicographic order. Who is with me on that? Okay. Now the key to see is that because we have an order, and because, even though it hurts, there is an order here and A comes first, all the A1s are together, all the A2s are together, and all the A3s are together. This is why if you use that index and you specifically look for example, A2, they're all in here. So this is a range. This is what I meant yesterday, saying A2 is actually a range between A2B1 and A2B4. Who sees that now? All right, so this is why if I do a query on just, that's called a prefix of the index, just A, then it's going to work, right? So this is why this also works, because here it's basically a range. So that would be a range on A. For example, A between 2 and 3 would be like this. But this, so this works. This doesn't work. And to see why this doesn't work, you have to see that here I'm querying on the second key of the index. Look what that means. The second key, they are not together. If you look for B1, they are spread all over with all the values of A. So this is not efficient at all. You cannot use the index. So it really only works if you query on A, right? So this is the reason. And more generally, what you should, as a take-home message, remember, is that whenever you build an index on a compound key, a tree index, it is as if you also had these indices here on prefixes. So if you have an index on ABC, it's as if you had an index on A, and it's as if you had an index on A and B. Just be careful with the 1 and -1 that you cannot change easily between the two in terms of ordering. But basically, this is the idea. It's as if. And this is something in practice that people make a mistake about. Because to give you some context, what happens in real life when you use MongoDB? You're going to store data in there, maybe terabytes of data, maybe even more. Typically, the people are not going to just query their data connecting to a JavaScript shell and issuing queries, right? So first you saw how the API is complex and so on. So in fact, what happens is that the API is invoked in a computer program. For example, you have a website that users access via the internet. And it is in these websites that you might have Node.js or Python or whatever language you use. And all the requests to MongoDB are in fact by programs. It's all automated with computer programs, right, to deal with that API. What that means is that given the websites that you have programmed, the queries that will reach MongoDB are usually following a specific pattern that depends on your website. For example, if you have a web shop, then the query pattern might be that a lot of people are searching for products and paginating like 10 by 10, right? If you're Digitech Galaxus, for example. So there are specific patterns. And so what happens is that when you set up your database system, you install MongoDB, the engineers, you in the future, will have to sit together and think, okay, what are the indices that we need to create for the website to function properly? And that means you have to figure out what are the queries that are commonly run by the computer program that you wrote for the website and set up the indices appropriately. This is a science and an art to do it. You need to understand the patterns. You need to have a reasonable number of indices. You cannot just go ahead and build 100 indices. That's not how it works. First, because that takes space. You don't have unlimited space on the drives. And second, because ideally, you would like the indices to fit in the main memory of the machine. It's more efficient if the index is in the main memory, because then you can directly follow memory pointers to look up in the index. So for this reason, you cannot build so many indices. A mistake that a lot of people make is that they will create an index on ABC, and they will also create an index on AB. That is a mistake because it's a waste of resources. If you understand that if you create an index on ABC, you get the one on AB for free, just because of this that I showed you here, then you can save memory, save resources, and just not even build an index on A and B. For whom is that clear? Right? So this is how it works. And this is on a case-by-case basis. It depends on your website. It depends on Node.js or Python code that you're going to write to issue the queries. And you have to just figure out the queries, that the indices that make it fast. Okay. So to summarize, what did we get with a document store like MongoDB? We got that now, if you have terabytes or petabytes of data, a point query, a lookup, is done in 2 milliseconds, just 2 milliseconds. You look it up in the index, O of 1 if it's a hash index, bam, 2 milliseconds. This is the magic. This is something we did not have with MapReduce and Spark because we were before in the data lake paradigm. With MapReduce and Spark, you have to do a full scan in parallel, yes, but still a scan. And that takes much more time than 2 milliseconds to do that. So this is the benefit of having a document store like that uses ETL to put the data in there. And the drawback in MongoDB is that you have an API, but you don't have a query language. And so this is why the next lecture is on query languages. And then you don't have these weird API arbitrary conventions that you saw yesterday, right? So you don't have to worry about these things anymore. And you can think on a higher level with a query language that actually is much like SQL, except that it's not for tables, it's for trees. Are there any questions on? Yes, I see over there.
Yes. So if we did index creation with like ABCD, would we also get? I assume we'd also get ABC for free. Would we then also get like AC, or how would that work?
Only prefixes. So if you do it on ABCD, you get A, you get AB, and you get ABC. The reason why you don't get A and C is because of this. If you look at A and C, you will have the same problem as is depicted here, just a bit more complex, right? Because then if you look for A and C, it's going to be spread all over the place because that might be for different values of B. And then you're back to the same problem. Does it make sense? Okay. So this is why I use the word prefix. It needs to be a prefix in the sense of a prefix of ABC, meaning just A or A and B. All right. Okay, then let's move on to the next part.